All right, thanks. Hello, everyone. Good afternoon for you. Good evening for me. Or actually, I think it's 7 p.m. for you, so you already call it evening, right? Which for me is just the afternoon. My name is Rodrigo, and I bring you a presentation today about NP-completeness. Sorry, NP-completeness, which is this very weird mathematical topic that I heard about a while ago, and I was thinking about it for the longest time because I knew like the definition, what it was supposed to mean, but I couldn't really understand it. Right? So today, hopefully when you leave not hopefully, today when you leave this presentation, you will know what NP completeness is and you'll be able to explain it to your friends. So that's the goal. Now, I assume you can see my screen. And throughout the presentation, feel free to ask questions. If you have any questions, feel free to ask them. But for now, I just want you to look at the screen and look at this gigantic expression because this is going to be very important. So I want you to take a look and remember this for later. Now I have a question for you folks. Do you want $1 million? Are you interested in... Is it... Lovely, right. I would also be interested in $1 million, and it's very easy to get $1 million. All you have to do is solve a maths problem that you can state with 5 letters. 5 letters, and you can state a problem that is worth $1 million. And that problem is the P versus NP problem. And as promised, there's 5 letters there. 1, 2, 3, 4, 5. 5 letters, $1 million. But what the heck is this P versus NP thing? What's this mathematical problem? Well, there's clearly 2 things going against each other, P and NP. So let's take a look at whatever P means. So let's see what this thing is. And to explain what this P is and what it stands for, I want to talk about... Oh, come on, someone in the chat saying 5 letters but 7 characters. Well, yes. But I said 5 letters, I didn't count the characters. And I mean, if you really want me to, I can delete the spaces and it will still be readable. So then it's 5 letters and 5 characters. Alright, so then let's look at what P means. Quick question for you, just to double check. Do you see a spotlight in front of the P with everything else grayed out? Ah, brilliant. Amazing. It's technology, folks. Technology is amazing. Alright, so then let's talk about trains. I'm in Portugal, I'm in Lisbon, and the second largest city in Portugal is called Porto. And Lisbon and Porto are 300 kilometers away, which is roughly 200 miles in freedom units. And let's say that a train departs Lisbon, or departs from Lisbon at a velocity of 100 miles per hour, and another train departs from Porto at 100 miles per hour. Now the question is, after how much time do the 2 trains meet? I'll give it a second. And hopefully you should be able to, if you didn't get there, you should be able to at least confirm that they do meet after 1 hour, because after 1 hour, the train from Lisbon already covered 100 miles, the train from Porto already covered 100 miles, and so they meet right in the middle. And the point of this train problem, which is a type of problem that real mathematicians solve every day in their daily work, is to show you an example of a simple problem that has an efficient algorithm that allows me to get to the answer. And this efficient algorithm really is just a simple calculation in this particular case. But when we're talking about P, the P from P versus NP, we're talking about problems in general, and the P stands for problems that have efficient algorithms to solve them. And at this point, I want to make a disclaimer. So throughout this presentation, I'm going to be a bit lenient with some terms. I will not be very, very rigorous. So I will sacrifice some formality for the sake of simplicity. All right. If by the end of the presentation you care about the nitty-gritty details and the formal definitions of everything, then we can talk about it. But for now, I will say some things that might not be strictly true if you take it literally. All right. But for now, we can think of a problem being in P. So the letter P actually stands for a set of problems, which is already a very weird way to start. P stands for a set of problems, and a problem is in P if you have an efficient algorithm to solve it. Now, this train problem was maybe a bit too simple, so let's take a look at something slightly less simple. Let's think about the problem of computing sums of numbers. If you have something like the sum of the list with only one item, where let's say that this is the Python code, but even if you don't write Python regularly, you should be able to tell me what this sum evaluates to. So the sum of a list with the number 1 should give 1. Hopefully no one is surprised by this. Now, say I want to compute this sum. What's the result of this? No. Sorry, where's my... No, okay. It's a type error because the ellipses cannot be added with 1 and 10. I thought this was a dynamic languages meetup. Maybe I'm in the wrong place. Yes, I am. I am getting back at you. No, but if I'm not trying to be funny, then you are right. It is 55, yes. And I'm not sure if you used a known shortcut, if you did the sum in your head. But what I want to think about when we think about this problem is the size of the list we're considering. And if you have two different lists, one with 10 elements and another one with 100 elements, then I don't really know how much time it will take to compute each sum. It's going to depend on my computer, your computer, however many processes I have running. But by looking at the fact that the second list is 10 times larger, I can infer that the time taken for the larger list will also be roughly 10 times larger. Because summing a list is something that we can do efficiently by going over the list. It's an operation it's an algorithm. Summing a list is something you can run in linear time. So an increase in size translates directly to an increase in time taken of roughly the same order of magnitude. So if we have now, say, a list of 200 elements, that means we're considering, or we're looking at a list that's twice as big, which means that we could expect the time taken to be also twice as large. Right? And this is another example of an efficient algorithm. So when we talk about efficient algorithms here today, we're talking about things that are linear or logarithmic or quadratic or actually, what's the word in English? To the power of 3. So things that are polynomials. If it's exponential, that's not okay. That's too bad. But if it's linear, quadratic, if it has logarithms in the middle, that's good enough for us. Now, am I making any sense? Do you folks have any questions you would like to ask at this point? All right. Oh, of course. Yeah. All right. So then a quick note. When we talk about efficient, we don't necessarily mean fast. Something might be efficient and still take a lot of time to run. When we think about efficient, we think about roughly a clever algorithm, something that's clever. Now, what if there's no efficient algorithm to solve a certain problem. Well, if that's the case, then we're talking about NP. Problems that don't have efficient algorithms may be in NP. So this NP is another set of problems, which is again a weird thing, sets of problems. I don't get it. But problems in NP don't have efficient algorithms to solve them. An example of a problem in NP is this graph 3 coloring problem, or in freedom spelling, graph 3 coloring. And this is a problem that I like because it's very, very visual. So let's say we have 3 colors, orange, green, and blue. And let's stick with these 3 colors throughout the rest of the presentation. And now let's say you have a very simple graph. 2 nodes or 2 vertices connected by a single edge. The graph 3 coloring problem asks if given this graph, you can color the vertices using the 3 available colors without having repeated colors across nodes that are connected. So we have 2 nodes, 3 available colors. Can you color the nodes without sharing colors across connected nodes? Yes, you absolutely can. For example, one node can be orange, the other can be blue. Fair enough. This was a very ridiculous instance of this problem. Now let's take a look at a slightly larger graph. There's 4 nodes here, there's 4 edges in total. Can you solve the 3 coloring problem for this given graph? Yes, you can. I like to ask questions and some of them are simple, alright? Don't be afraid. Yes, this is one possible coloring. There's others. Now let's take this up a notch. What about this graph? You're right. You cannot, because whatever you do with the top 3, you have no colors left for the bottom one. So this is an instance, or this is an impossible instance of this problem. Alright, fair enough. That's okay. Now what if you have a graph like this? Sorry, what was the argument I heard back there? Alright, well, you don't need... So you might be thinking that because you don't have a structure like this with 4 nodes that are completely connected, then it's possible. But you can have, there exist graphs that do not have this structure, 4 nodes connected completely, that are impossible. So in order to check whether this is possible or not, well, you have to either find a coloring that works or prove to me that no coloring works. But other than our guesses, we don't really know, just by looking at the graph. And the truth is, this graph 3 coloring problem has no efficient algorithm to solve it. Now, why not? Well, there's 2 possible scenarios. Either all of us humans haven't been clever enough to find an efficient algorithm to solve it, so the algorithm exists but we don't know what it is, or there simply is no efficient algorithm to solve this. And this is the P versus NP problem. The question is, for the NP problems, which we can colloquially say they're hard because they don't have efficient algorithms that solve them, are these problems hard because they really are hard, or because we haven't figured out how to solve them efficiently? So is P different from NP, or are they both the same set? So this is the question. This is the problem, P versus NP. Again, roughly speaking, I'm bending some corners here. And for this NP problem, the best you can do is to try every possible coloring until you either find one that works or exhaust all of your possibilities and conclude that none works. Am I making sense so far? But I'm okay with that. Okay, so this was one example of a problem that is in this NP set. But let's take a look at the second one. This set problem. Now this SAT, these are not the... I think you have some standardized tests in the United States of America that also go by SAT, right? Yeah, this is not that, okay? It's a different SAT, and this usually spell out SAT for satisfiability, short for satisfiability. Now this is another very interesting problem, but instead of having 3 colors to work with, we have the 2 Boolean values, true and false. And I was going to do the obvious thing of using green for true and red for false, and then I realized that some colorblind people have a hard time distinguishing red and green. So the idea here is the yellow stands for kind of a light bulb that's turned on, and the black is a light bulb that's turned off. If you don't like my choice of colors, then chat with me later, because I also don't know if I like it. But this is what we're going with. So this is true and false. And now what we have, instead of having a graph, is a Boolean expression. And P and Q here are 2 different Boolean variables. Now the set problem, the satisfiability problem, asks, is there a way to make assignments to the variables such that the overall expression or the overall formula evaluates to true? And so now I ask you folks, for this Boolean expression, can I assign... Yeah, both true works, yes. True and true is true. So they have to be both equal and both true, yes. For this expression, this is the assignment that works. Now let's try another one. Let's do P or not P. Yes, this also works. You could set P to true, and now on the right you have not true, which becomes false. But that's fine, because true or false is still true. But what's the play I was making here was that it actually doesn't really matter, because if you set P to false, then the not false on the right becomes true, and you still get true as the final result. But fair enough. I mean, you can satisfy it with whatever assignment you pick. Now, what if I have the formula P and not P? What do you mean false? Sorry. I'm sorry, can someone translate what Catherine said? I'm sorry. It sounded like that, but I wasn't sure, so I just wanted to double check. Right, so regardless of what you do, and let me duplicate the expression here. Regardless of whether you set P to true or false, you're going to end up with an AND with a true on one side and a false on the other side, and we know that true and false, and also false and true, are both false. So I think what you meant when everyone said false, you meant that this was not satisfiable, right? Yeah, that's what I thought. And Catherine said, Evelyn, you're right because you're awesome. But that's what we all meant. All right. And again, this problem, this set problem, has no efficient algorithm. there's no efficient algorithm to solve the set problem in general. Of course, we looked at small formulas and you looked at them and you knew the answer. But in general, for an arbitrary formula, there's no efficient algorithm to solve it. Now the question is, why not? And again, there's only one of two scenarios. Either we haven't found an efficient algorithm, or simply there isn't. And as of today, the best you can do is to try every single possible assignment. And you either find one that works, or you don't. Now, small caveat here, for the 3-coloring problem, for the set problem, and for other problems in NP, there aren't efficient algorithms. It doesn't mean we cannot solve these problems in practice. Alright? We can devise algorithms that use heuristics to try and make the best out of smaller patterns we can recognize and smaller instances or structures we understand. So these problems can still be solved in practice in some cases. It's just the general case that we don't know how to solve efficiently. Am I making sense so far? Everyone okay with this? Alright. Now I think we're going to get into the most interesting part. This is where the fun really begins. So there's this thing, there's a but here. The set problem has a very interesting property. And the interesting property is what's in the title of the presentation. So the problem set is NP-complete. Whatever this means, right? Whatever this means. And what I want to help you understand is exactly what NP-complete means. Now, roughly, this is not the helpful part, but I need to start here. Something is NP complete, or in particular, SAT being NP complete means that any other NP problem can be translated to SAT. I know this makes no sense. It's okay. This is what I knew, quote unquote, for years. So I could replicate the sentence, but I didn't really understand it. Let's just go over it again. SAT being NP complete means that any NP problem can be translated to SAT. But what the heck does this sentence mean? SAT. Let's try to understand what this translation thing means. Can you clicker? Yes. So let's talk about translations. And to talk about translations, I want to go back to the train problem for a second, if you folks don't mind. So Lisbon and Porto are 200 miles apart. A train departs from Lisbon at 100 miles per hour, another one from Porto at the same speed, and I was asking when do they meet. Now let's say that the answer, let's call it T, for time. The time it takes for the two trains to meet. And now what I want to do is I want to take a look at the numbers that we care about, the distance and the speed of each train, and just color code them. The way you solve this is by taking the speeds, multiplying them by the unknown time, which should total the total distance they have to cover. And now you rearrange the equation, you put the t out, you add the two numbers, and then you can move the numbers on the other to the other side and divide, and that's how you get to the 1 hour answer, because 200 divided by 200 is, surprise, surprise, 1. Now this is a lot of overhead for such a simple instance, but what this shows you is the overall method, the overall solution. If you have different numbers, you just plug them into the same expression and you get the results. And what we did here was take words, the problem statement written, spelled out with words, and we translated it into a mathematical expression. And so what I was saying before is that I can take any NP problem and I can translate it to set, right? But this is a very weird, I haven't done anything useful yet. This is still a very weird statement. So instead of thinking about any NP problem, instead of thinking about all of them, the factorization, the ones we don't even know about, let's focus on a single NP problem that we already kind of understand. And now let's push this to the side. What we want to do is take the graph 3 coloring, this problem, and we want to think about the color restrictions that make up the problem. And when we think about the set problem, a set problem really is just about Boolean expressions, finding assignments that satisfy Boolean expressions. So what we want to do is turn these color restrictions into equivalent Boolean expressions. This is our goal. Can you hear my dog losing his mind? It's all right. Okay, so do you want to ask questions about this? My dog was complaining about something else, not about this diagram. All right, exactly, because this is what's going to be fun. You know, it's this translation is going to be fun. I'm a weird person, so when I say something is fun, you have to take that with a grain of salt. But this is going to be fun, right? So now let's look back on the graph 3 coloring problem and think about the restrictions that the problem has. And there's 2 of them. So each vertex has one color from the 3 colors we picked, orange, green, and blue, and then connected vertices cannot share a color. These are the restrictions. Correct? Now, what we need to do is turn each of these restrictions into one or multiple Boolean expressions. So let's start from the beginning. Let's just look at the part each vertex. So let's see how to turn each vertex into a Boolean expression, or how we're going to encode each vertex. So for now we'll work with a very, very simple graph, all right? And I couldn't make it, I could make it simpler by removing B and the edge, but then it wouldn't be any fun. So let's go with this one. For each vertex, I'm going to create 3 variables. And for vertex A, I'm going to call them AO, AG, and AB. And the idea is variable AO tells me whether the vertex A is orange or not. Variable AG tells me whether the vertex A is green or not. And variable AB tells me whether A will be blue or not. And someone points out very astutely that these were on my first slide. Well, that's wrong, it was the second slide. The first slide was the title slide. But yes, these variables showed up early. So we're getting close. Now, you know, the only thing better than me making bad jokes is folks reacting to my bad jokes. I really appreciate it. Thank you. Thank you, everyone. All right. The idea here is if a variable is true, then it's telling you that the respective vertex has that given color. For example, if AO is true, then vertex A is orange. If AB is true, then vertex A is blue. My brain stopped working for a second there because I was confused by my next slide, but everything is okay, folks, don't worry. So this is how we're going to think of each vertex. But we were only halfway through the sentence. The restriction is each vertex has one color. This is the restriction. So what we need to do is we need to take our 3 variables for vertex A and put them together. And if you write something like AO or AG or AB, then this Boolean expression, the whole thing together, is only true when the vertex A has a color. So this essentially forces, so this Boolean expression forces the node, the vertex, to have a color, to be colored. Is it making sense? Excellent. But there's a problem here, because if I set two different variables to true, the full expression is true, and I can't have a vertex with two colors or three. I can't have that. So in reality, when I think of my restrictions, I can't really say that each vertex has one color. What I did now was restrict each vertex to have at least one color. So I am forcing at least one color on each vertex, but I also want each vertex to have at most one color, because I want this is, if you look at it, this is a very convoluted way of saying each vertex has exactly one color. It has at least one and at most one. How do we sorry, can you say that again? It kind of does. It kind of does. It has that feeling. Yes. Yeah. It sounds unnecessarily complicated, but in this case, there's no way around it, unfortunately. So, so in the previous example, we had. All right, I couldn't get all of it, but I felt like your answer sounded more or less plausible. So I think you folks are on the right track. I am going to add more stuff to this expression, and one thing that's important to note is that the objective, the end result that we're looking for, is a Boolean expression that somehow represents the three coloring problem, so that they are equivalent. If I find an assignment that satisfies the formula, I can immediately extract a coloring for the graph. And if the graph has a coloring, I can immediately create, or I can immediately find the assignment that satisfies the formula. So we have to be very strict with the formulas we write, because a couple of slides ago, this is not okay. I cannot have a vertex with two colors, so I need to add more stuff to my formula to stop this from happening. No, jumping ahead is good because it means you're on the right track. You're just going too fast. All right, let's do the following. Let's where is it? Let me show what I'm about to write below, and maybe we will have a slightly more complete picture that's going to help. And then even if it doesn't make a lot of sense yet, the folks that are sitting there with you can help, and so can I. So the problem with the slide we were on was that I had two variables with the same two variables that were true, which kind of imply that a single vertex has two colors. I don't want that. So what I can say is hey, I want AO or AG, but also I do not want both at the same time. AO or AG or AB. So A is orange or green or blue, and also not orange and green at the same time. But this needs to be completed further. I also need to say, and I do not want orange and blue on the same vertex. And, by the way, I do not want green and blue on the same vertex. My next slide, right? So now connected vertices. So we've taken a look at a single vertex, and I only showed you the expression for A, but you can do the same thing for B and for however many vertices you have independently. But then there's relationships among the vertices. And you know that connected vertices they cannot have the same color. So now you need to add a couple more expressions that translate this restriction into, or that take this restriction to the world of Boolean expressions. So let's keep looking at our AB graph. Vertex A needs 3 variables. So does vertex B. I need 3 variables as well. But now what I want to say is that A and B cannot have the same color. So I cannot have A of O and B of O at the same time. I cannot. And also, I cannot have A of G and B of G. I cannot. And by the way, also, in case you weren't expecting it, I cannot have A of B and B of B at the same time. I simply cannot. Because that's how I want my graph to look like. I want adjacent vertices to have different colors, which means the variables that pertain to the same color cannot be true at the same time. So this big Boolean expression stops that from happening. Great. Now, these were just separate pieces of the full problem, right? So we've taken a look at the 3 restrictions more or less individually. The first 2, each vertex has at least 1 color and each vertex has at most 1 color. This is lawyer speak for each vertex has exactly 1 color. The reason we split them is because in the world of Boolean expressions, we need to be more verbose to be able to encode this restriction in a Boolean expression. So we split the 2, and then also the connected vertices cannot share a color. So if we take everything and we put everything together, for this simple graph with 2 nodes and a single edge, the big, complete Boolean expression is 4 lines that just encode the state of vertex A, plus 4 lines that just encode the state of vertex B, plus 3 lines that encode the relationship between A and B, because there is an edge. So if you translate the 3 coloring problem at the top of is there a way to color vertices A and B with 3 colors such that they don't share a color, if you take that 3 coloring problem, you can turn it into a set problem that looks exactly like this big Boolean expression. Now what you want to do is solve the problem in set land. So you grab your 6 variables. Sorry, is there a question? Oh, okay, get it. I get it. So now if you're in set land, you want to solve the set problem, which means looking at the 6 variables you have on the right and find an assignment that satisfies the big formula on the left. This is the set problem. Boolean formula, Boolean variables. Now, if you do something like, for example, setting the top 2 variables to true and the other 4 to false, this does not work, because there is a clause at the bottom that evaluates to false. AO and BO are true, so AO and BO is true. You factor in the not, this is false, and suddenly you have a false inside your chain of ends, and. So you know that this will evaluate to false. It doesn't work. Does everyone agree that this doesn't work? All right. Now, something that would work, for example, there's plenty, would be to say A of O is true, B of B is true, and everything else is false. If you work through the Boolean expression on the left, and if you evaluate it and you don't make any mistakes like I would if I was doing it by hand, you will see that the full expression evaluates to true. Okay, you solved the set problem. Now, we were doing all of this because we want to translate the graph coloring to the set problem. Now that we solved it in the set, in the world of set, we want to go back to colors. We want to extract our coloring solution from the Boolean assignment. So what we do now is we go column by column and see what color each vertex gets. If A of O is true, that means A should be orange. And if B of B is true, that means B should be blue. Questions about this? Okay. Why the heck would you do this? Why do you want such a big Boolean expression when it's obvious that any two colors would work as long as they're different? Excellent question. Remember that... Sorry? Any graph, absolutely any graph, if a graph is larger, more complex, this works. But also, remember that NP-complete means any NP problem can be turned into a set problem. And not all NP-complete problems look nice like this graph, right? All right, let's okay, sorry, I got lost for a second. That and this process of finding Boolean assignments that satisfy certain Boolean expressions is, again, difficult because there's no efficient algorithm. However, there are very clever programs written by very clever people called set solvers that are specialized in solving these kinds of problems. And so they look for all sorts of heuristics and structure and patterns that you can leverage to be as clever as possible when solving this problem, making it practical to solve whatever problems you want after you translate them to set. So that's very, very cool. Now, this was a very small graph, not very interesting. So how about we go back to the original graph for which we didn't know if it was 3 colorable or not? Some of you guessed yes. I couldn't hear if anyone guessed no, but we couldn't really tell, right? So the obvious thing you do is then you write the huge expression from the second slide that encodes the graph as a set problem. You pass this to a set solver, and you let the set solver do its magic, and it either says there is an assignment or there isn't. And in this case, it does give you a valid assignment. Something like this would work. So the folks who guessed yes were correct. Now I see that for the future, I need to have a graph here that doesn't work, so that folks can just say, yes, of course. So I need to change this example, I think. But this is it. Instead of me having to go through all of the different colors, what I did was I wrote a short Python script, I listed the edges, the script generated the expression, I passed it to a set solver, I got the assignment, and from there I could extract the colors. And now, if you want the $1 million from earlier, one thing you could try to do is find an efficient solution for the SAT problem, because if there is one, if you can find an efficient algorithm for the SAT problem, because you can translate any other problem into SAT, you get for free efficient solutions for all other problems, right? And in the P versus NP dilemma, you would discover, or you would prove rather, that NP is actually the same as P. So that would grant you $1 million. Now, unfortunately, most mathematicians think that's not the case, so you can't. They believe that P and NP are actually different, and so there is no efficient way of solving SAT. It doesn't exist. Now you have to prove it doesn't exist, which is really weird. How do you prove that there is a problem for which you cannot possibly build an efficient solution? Very interesting. Can I interest you in one more weird fact? I hope you're sitting for this. So, the satisfiability problem is NP-complete, but so is the graph 3 coloring. So you can take any NP problem, encode it into a graph, and finding a valid coloring means you found a valid solution for the original problem. So if you think this was kind of confusing, turning a graph coloring problem into a set expression, just wait until you Google how to do the reverse. Take a set expression and turn it into a graph. I was looking at it earlier, and I gotta say that my brain suffered. But it's something very interesting for you folks to look up later if you're into this kind of suffering. All right, everyone. This has been a blast. I love talking about weird stuff. Thank you so much for bearing with me for the better part of, is it 1 hour and a half by now? I think so. No, of course. I've done worse. I've done worse in the name of science. Don't worry. All right, folks. No, I had a lot of fun. I hope you enjoyed it as well.